The barber paradox is one of the most famous and mind-bending puzzles in logic. It sounds simple at first, but it hides a problem that even mathematicians struggle with. Imagine a small town with a barber who has a very specific rule. He shaves all the men who do not shave themselves, and only those men. Now here's the question. Does the barber shave himself? If he does shave himself, then he breaks the rule, because he only shaves men who don't shave themselves. But if he doesn't shave himself, then he still breaks the rule, because he is supposed to shave every man who does not shave himself. No matter what you decide, the rule collapses into a contradiction. It seems like a simple question, but it cannot be answered, not without breaking logic itself. This paradox was introduced by Bertrand Russell to show a deeper problem in mathematics and logic, the problem of self-reference, where a rule or definition refers back to itself. It is the same issue that appears in set theory. With the set of all sets that do not contain themselves, the barber paradox teaches us something profound. It shows that even the simplest rules can create impossible situations. When definitions turn back on themselves, they can collapse entirely. It's not really about barbers. It's about logic, reasoning, and the limits of language. A question that seems harmless at first slowly reveals the hidden complexity of thought itself. So next time you think a rule is simple and clear, think again. Sometimes, even the most ordinary rules can lead to extraordinary contradictions. The barber paradox is more than a puzzle. It is a lesson in thinking carefully about what we define and how we define it. The crocodile paradox is one of the most intriguing puzzles in logic. It sounds simple at first, but it hides a problem that even philosophers struggle with. Imagine this. A crocodile steals a child and approaches the parent with a very strange promise. I will return your child, if and only if you correctly predict what I will do next. At first, it might seem straightforward, but then comes the real puzzle. Suppose the parent says, "You will not return my child." What should the crocodile do if the crocodile does not return the child? Then the parent's prediction turns out to be correct, and according to his own promise, he should return the child. But if the crocodile does return the child, then the parent's prediction is wrong, and again, according to the promise, he should not return the child, no matter what the crocodile decides. The situation collapses into a logical paradox. It is impossible to satisfy the condition, and yet the promise itself cannot be broken without contradiction. This paradox is not about crocodiles at all. It is about self-reference, conditional statements, and the hidden traps in reasoning. It shows how even the simplest rules or promises can create situations that are impossible to resolve. Philosophers have used it to explore concepts like truth, prediction, and logic. It reveals the subtle ways language and reasoning can conflict with themselves. The crocodile paradox reminds us that logic is fragile when statements refer to themselves, and sometimes a simple question or promise can unravel into a puzzle that has no solution. The grandfather paradox is one of the most famous puzzles in time travel. It raises questions about causality, choice, and the very nature of time itself. Imagine this. You somehow travel back in time, and you meet your grandfather before he has any children. Now, suppose you do something that prevents him from meeting your grandmother, or worse, something that prevents him from having children at all. Here's the paradox. If your grandfather never has children, then one of your parents is never born. And if your parent is never born, then you are never born either, which means you could never have traveled back in time in the first place. But if you never traveled back in time, then your grandfather's life remains unchanged, and you are born as usual, which means you could travel back in time. No matter how you look at it, the situation creates a loop that cannot be resolved. Actions in the past affect the future, but the future is needed to allow those actions in the first place. The grandfather paradox is a striking example of the challenges in understanding time travel. It shows that messing with the past can lead to contradictions that break the logic of cause and effect. Physicists and philosophers have debated solutions for decades. Some suggest that changing the past is impossible. Others propose parallel universes, where your actions create a new timeline instead of affecting your own. At its core, the grandfather paradox reminds us that time is not just a simple sequence of events. It is a delicate web of cause and effect, and tampering with it, even in thought experiments, can lead to impossible contradictions. The preface paradox is one of the most subtle and fascinating puzzles in logic and belief. It comes from a problem that authors often face when writing a book. Imagine this. An author carefully writes every chapter of a book. She checks each fact, verifies each argument, and believes that everything she has written is true. But then, in the preface of the book, she writes something curious. She admits that despite her careful work, there might be errors, some mistakes that escaped her notice. Here's the paradox. In each chapter, the author believes the statements are true. Yet, in the preface, she also believes that at least one statement might be false. How can both beliefs coexist? If she believes each statement individually is true, then shouldn't she believe the whole book is true? And yet she also believes there is a chance of error, a possibility that contradicts her confidence in the individual statements. The preface paradox shows a tension between local belief and global belief. Believing each part can be true does not always allow you to believe that everything as a whole is true. Philosophers use this paradox to explore rationality, uncertainty, and consistency. It highlights the limits of human reasoning and the challenges of holding multiple beliefs at once. At its core, the preface paradox reminds us that even careful knowledge is fragile. Even when we are confident in individual truths, our awareness of human error forces us to accept uncertainty, and that tension is what makes rational thought both powerful and puzzling. The two envelopes paradox is one of the most famous puzzles in probability and decision-making. It challenges our intuition about risk, choice, and expectation. Imagine this. You are presented with two envelopes. Each envelope contains money. One envelope contains twice as much as the other. You do not know which is which. You pick one envelope at random. And now comes the tempting question. Should you keep it or switch to the other envelope? Here's the reasoning that creates the paradox. Suppose the envelope you picked contains an amount x. Then the other envelope could either contain 2x or x divided by 2. If each possibility is equally likely, the expected value of switching seems to be higher than keeping your envelope. But wait, if the expected value is always higher by switching, then no matter which envelope you pick, it always seems better to switch. And that creates a strange loop. You could keep switching forever, thinking you are always improving your outcome. This paradox highlights the problems of expectation, probability, and reasoning under uncertainty. Mathematicians have debated it for decades. Some argue the flaw lies in the assumptions about probability. Others say it shows the limitations of expected value calculations when applied naively. At its core, the two envelopes paradox is a reminder that our intuitions about chance and value can be misleading. A choice that seems simple can hide hidden contradictions in logic and probability. And that is why this puzzle continues to fascinate mathematicians, philosophers, and decision theorists alike. Russell's paradox is one of the most famous and profound puzzles in mathematics and logic. It reveals a hidden problem in how we define sets and challenges the foundations of mathematics itself. Imagine this. You have a set, a collection of things. Some sets contain themselves as members and some sets do not. Now consider the set of all sets that do not contain themselves. Does this set contain itself? Here's the paradox. If the set contains itself, then by definition it should not be in the set, because it only contains sets that do not contain themselves. But if the set does not contain itself, then it fits the definition of the set, because it only contains sets that do not contain themselves. No matter what you decide, the situation collapses into a contradiction. This simple definition creates an impossible loop, a set that cannot consistently be said to exist or not exist. Russell discovered this paradox in the early 20th century. It shook the foundations of set theory and mathematics as a whole. Mathematicians had to rethink the way sets are defined, and this led to the development of more rigorous systems of logic, like Zermelo-Fraenkel's set theory. At its core, Russell's paradox is a lesson in the limits of naive reasoning. It shows how self-reference can create contradictions, and how careful we must be when defining the basic building blocks of mathematics. Even a simple, seemingly harmless rule can unravel into a logical nightmare. Russell's paradox reminds us that logic and mathematics, while powerful, are not immune to subtle traps. The potato paradox is one of the most surprising and counterintuitive puzzles in mathematics. It sounds simple at first, but it can completely twist your intuition about percentages and weight. Imagine this. A farmer has 100 kilograms of potatoes. These potatoes are made up of 99% water and 1% solid matter. Now, the farmer leaves the potatoes out to dry. The water evaporates and the potatoes are now 98% water. Here's the question. What is the new total weight of the potatoes? At first, you might think it should be close to 99 kilograms, maybe losing just a little water. But the answer is shocking. The potatoes now weigh only 50 kilograms. Why? Because the solid part of the potato still weighs the same, 1 kilogram. If that 1 kilogram now represents 2% of the total weight, the total weight must be 50 kilograms. This paradox teaches a powerful lesson. It shows how percentages and proportions can be extremely misleading. Even small changes in percentage points can create huge changes in total quantity. The potato paradox is simple to state, yet mind-bending to solve. It challenges our intuition and reminds us to think carefully about ratios, percentages, and how numbers relate to each other. In the end, what seems like a trivial calculation turns into a puzzle that surprises even the most mathematically minded. And that is the potato paradox. The twin paradox is one of the most famous and fascinating puzzles in physics. It comes from the strange world of Einstein's theory of relativity. Imagine this. There are two twins. One twin stays on Earth, living an ordinary life. The other twin boards a spaceship, traveling at speeds close to the speed of light. Here's where the paradox begins. According to Einstein's theory of special relativity, time slows down for objects moving at high speeds. This means the traveling twin experiences time more slowly than the twin who stays on Earth. When the traveling twin returns home, something incredible happens. The twin who stayed on Earth has aged normally, but the traveling twin is much younger. This seems impossible at first, because from the traveling twin's perspective, it could be argued that the Earth is moving instead. So shouldn't the Earth twin age more slowly? The resolution lies in acceleration and reference frames. The traveling twin experiences acceleration when turning around to return to Earth. This breaks the symmetry and makes the situation consistent with relativity. The twin paradox is more than a puzzle. It demonstrates that time is not absolute. It can stretch, shrink, and flow differently depending on motion and gravity. It challenges our everyday intuition and shows that the universe is far stranger than it seems. Even a simple thought experiment with twins can reveal the deep and counterintuitive nature of reality. At its core, the twin paradox is a powerful illustration of how relativity changes our understanding of time, space, and aging. It reminds us that the universe does not always follow the rules we expect. Moore's paradox is one of the most curious puzzles in philosophy and logic. It deals with statements that seem perfectly grammatical, yet are paradoxical when asserted. Imagine this. Someone says, "It is raining, but I don't believe that it is raining." At first, the sentence sounds fine. It is grammatically correct. It expresses a coherent thought. But when someone actually asserts it, something strange happens. It becomes absurd. even though there is no logical contradiction in the content itself. Here's the paradox. Why is it strange to say something like, "It is raining, but I don't believe it is raining," out loud? Because assertion implies belief. When you assert a statement, you are committing yourself to believing it. And yet in the sentence, you explicitly deny that belief. Moore's paradox highlights a gap between truth and our attitudes toward truth. It shows that you can have a statement that is logically consistent, yet impossible or irrational to sincerely assert. Philosophers use it to explore the nature of belief, knowledge, and language. It reveals subtle limits of what we can consistently say and claim, even when the words themselves are grammatically and logically correct. At its core, Moore's paradox teaches us that human reasoning and language are more fragile than they appear. It reminds us that truth alone is not enough. Our beliefs, assertions, and attitudes must also align. And that is the strange, fascinating lesson of Moore's paradox. The paradox of free will is one of the oldest and most profound questions in philosophy. It challenges our understanding of choice, responsibility, and the nature of the universe itself. Imagine this. You believe that humans have free will, that you can make choices independently. You can decide what to do, plan your actions, and shape your own destiny. But then consider this. If the universe follows deterministic laws, if every event is the inevitable result of prior causes, then your choices may not truly be free. Everything you do might be predetermined by prior states of the world. Here's the paradox. If our actions are determined, can we really be said to have free will? But if our actions are not determined, if they are completely random, then our choices are not really ours either. They are just random events without meaning or control. The paradox of free will lies in this tension. True freedom seems impossible under strict determinism. Yet true freedom also seems impossible under pure randomness. Philosophers have debated this for centuries. Some argue for compatibilism, the idea that free will can exist even in a determined universe. Others argue for libertarian free will, insisting that we must have genuine choice to be morally responsible. At its core, the paradox forces us to confront a deep question. How can we truly be agents in the universe, if the universe itself constrains or randomizes our actions? It challenges our intuitions about morality, responsibility, and the very meaning of human life. The paradox of free will reminds us that freedom is not simple. It is a concept intertwined with physics, philosophy, and our understanding of time and causality. And it continues to puzzle thinkers, even today. The nocebo effect paradox is one of the most fascinating puzzles in medicine and psychology. It shows how our beliefs and expectations can shape reality in ways that seem almost impossible. Imagine this. A patient takes a harmless pill. They are told it may cause side effects, headache, nausea, or fatigue. Even though the pill has no active ingredient, the patient may start experiencing those very symptoms. Here's the paradox. The body reacts to what the mind believes. A non-existent threat becomes real. The expectation of harm produces actual harm. But here's where it gets stranger. The patient knows the pill is harmless, yet their mind convinces their body otherwise. Belief alone becomes a force powerful enough to trigger genuine physiological responses. The nocebo effect paradox highlights a mysterious connection between mind and body. It challenges the traditional idea that medicine works only through chemistry or biology. It shows that perception, expectation, and attention can actively shape outcomes. Philosophers and scientists use this paradox to explore questions about consciousness, causality, and control. If believing something can make it true, even temporarily, where do the boundaries of reality lie? How much of our health and experience is shaped by what we anticipate or fear? At its core, the nocebo effect paradox reminds us that the mind is not a passive observer of reality. It is an active participant, capable of creating outcomes simply through expectation. And that is why this paradox continues to fascinate doctors, psychologists and philosophers alike. The prisoner's dilemma is one of the most famous puzzles in game theory and decision-making. It reveals the tension between individual self-interest and collective benefit. Imagine this. Two criminals are arrested for a crime. They are interrogated separately and cannot communicate with each other. Each prisoner faces a choice: cooperate with the other by staying silent, or betray the other by confessing. Here's the dilemma. If both prisoners stay silent, they get a light sentence. If one betrays while the other stays silent, the betrayer goes free, and the silent one gets a heavy sentence. But if both betray each other, both get moderate sentences. At first glance, it seems obvious to betray the other. After all, betrayal maximizes your own benefit no matter what the other does. But here's the paradox. If both prisoners think this way and betray each other, they end up worse off than if they had both cooperated. The prisoner's dilemma teaches a profound lesson. Individual rationality can lead to collectively irrational outcomes. It shows why cooperation is often difficult, even when it is clearly in everyone's best interest. This paradox is not just a thought experiment. It applies to economics, politics, and everyday life. From business competition to environmental policy, to personal relationships, the tension between self-interest and cooperation is everywhere. At its core, the prisoner's dilemma challenges us to think beyond immediate gain. It asks us to consider trust, communication, and the long-term consequences of our choices. And it remains one of the most powerful tools for understanding human behavior, strategy, and morality. The birthday paradox is one of the most surprising puzzles in probability and statistics. At first, it sounds impossible, but the math tells a different story. Imagine this. You are at a party with 23 people. Now here's the question. What is the chance that at least 2 people share the same birthday? Most people guess it is very low, maybe 1 in 100. But here's the shocking truth. The probability is actually over 50%. Why is this so counterintuitive? It's because the paradox is not about matching your birthday with someone else's. It's about any pair of people matching. And there are many possible pairs in a group of 23. The number of comparisons grows quickly, and the probability rises much faster than our intuition expects. The birthday paradox teaches us a profound lesson about probability. Our brains are not naturally good at estimating likelihoods when many combinations are involved. Even a small group of people can produce surprising results. This paradox has real-world applications, from cryptography and hashing algorithms to understanding coincidences in social settings. It shows how seemingly improbable events are much more likely than they appear. At its core, the birthday paradox reminds us that probability can be counterintuitive. It challenges our assumptions about chance and reveals the hidden patterns in randomness. And that is why this paradox continues to fascinate mathematicians, scientists, and curious minds alike. Newcomb's paradox is one of the most fascinating puzzles in decision theory and philosophy. It challenges our understanding of prediction, free will, and rational choice. Imagine this. There is a powerful predictor. Some say it can predict human behavior with near-perfect accuracy. You are presented with 2 boxes, one transparent, containing $1,000, and one opaque, which may contain either $1 million or nothing. You have a choice: take both boxes, or take only the opaque box. Here's the twist. The predictor has already made its prediction. If it predicted you would take only the opaque box, it has placed $1 million inside. If it predicted you would take both boxes, it has left the opaque box empty. Now comes the paradox. Do you take only the opaque box, trusting the predictor's accuracy? Or do you take both boxes, reasoning that the opaque box already contains whatever it will contain? No matter how you reason, each approach seems rational. One strategy maximizes expected gain based on prediction. The other maximizes gain based on the current contents of the boxes. Newcomb's paradox highlights a deep conflict between 2 ideas: causal reasoning and evidential reasoning. It questions whether our choices can be free if they are predictable, and whether rational decision-making depends on prediction or outcome. At its core, this paradox forces us to confront the tension between knowledge, trust, and action. It shows that even simple choices can become deeply complex when prediction and expectation come into play. And that is the enduring mystery of Newcomb's paradox. The Fermi Paradox is one of the most profound and unsettling questions in science and philosophy. It asks a simple question, and yet the answer is deeply mysterious. The universe is vast, containing hundreds of billions of stars in our galaxy alone. Many of these stars have planets, some of which could be capable of supporting life. Given the sheer number of stars and planets, it seems almost certain that intelligent life should exist elsewhere. And yet, we see no evidence of it. No signals, no artifacts, no signs of advanced civilizations. This is the paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" Scientists have proposed many possible explanations. Perhaps intelligent life is extremely rare, or civilizations self-destruct before they can communicate. Maybe advanced civilizations deliberately avoid contact. Or perhaps we are simply looking in the wrong way, at the wrong time, or with the wrong technology. The Fermi Paradox challenges our assumptions about life, the universe, and our place within it. It forces us to confront the possibility that we might be alone, or that the universe is teeming with life that we cannot perceive. At its core, the paradox is a reflection on existence itself. It is a question about probability, survival, technology, and the limits of human knowledge. And it leaves us with a humbling thought. The universe is vast and silent, yet it may contain countless mysteries we are only beginning to imagine. The quantum suicide paradox is one of the most mind-bending thought experiments in quantum physics. It challenges our understanding of reality, consciousness, and the very nature of existence. Imagine this. A scientist sets up a machine connected to a quantum event. The machine is rigged so that every time the quantum event occurs a certain way, the scientist survives. But if it occurs the other way, the scientist dies instantly. Now, according to the many worlds interpretation of quantum mechanics, every quantum event splits the universe into multiple branches. In some branches, the scientist survives. In others, they do not. Here's the paradox. From the scientist's own perspective, they will always find themselves surviving, because in any universe where they die, they are no longer conscious to observe it. This seems to create a bizarre situation. It implies that subjective experience might persist indefinitely, even in the face of events that would normally be fatal. It challenges our intuitions about probability, mortality, and what it means to be conscious. The quantum suicide paradox raises deep philosophical questions. Can consciousness track one's survival across multiple worlds? Does it make sense to speak of dying if in some branches of reality you always continue to exist? At its core, this paradox highlights the strange and counterintuitive consequences of quantum mechanics. It blurs the line between physics and philosophy, and it forces us to reconsider the relationship between observation, reality, and the self. The quantum suicide paradox is more than a thought experiment. It is a glimpse into a universe far stranger than our everyday experience suggests. The black hole information paradox is one of the most mysterious puzzles in modern physics. It sits at the intersection of quantum mechanics, relativity, and our understanding of the universe. Imagine this. A star collapses under its own gravity, forming a black hole, a region of space so dense that nothing, not even light, can escape its pull. According to classical physics, anything that falls into a black hole is lost forever. The information about the particles, their states, and their properties seems to disappear completely. Here's the paradox. Quantum mechanics, the fundamental theory of particles and information, tells us that information can never be destroyed. But black holes appear to violate this principle. If information truly vanishes inside a black hole, then the laws of quantum mechanics are broken. Stephen Hawking famously proposed that black holes emit radiation, now called Hawking radiation. Over time, the black hole can evaporate completely, and yet the information about what fell in seems to be lost forever. This paradox has puzzled physicists for decades. Some suggest that information is somehow encoded in the radiation. Others propose that it is stored at the black hole's surface, in what is known as the holographic principle. Or perhaps we have yet to fully understand the connection between gravity and quantum mechanics. At its core, the black hole information paradox challenges our understanding of reality itself. It forces us to question the nature of information, the laws of physics, and the ultimate fate of matter in the universe. The paradox reminds us that even the most extreme objects in the cosmos follow rules we are still trying to comprehend, and that the universe may be far stranger and more intricate than we can imagine. The Boltzmann brain paradox is one of the most unsettling and mind-bending ideas in cosmology and philosophy. It challenges our understanding of probability, reality, and even our own existence. Imagine this. The universe exists for an incomprehensibly long time. Over billions or trillions of years, random fluctuations can occur in the fabric of space and matter. Now, according to some interpretations of statistical mechanics, it is theoretically more likely for a single, fully formed brain, complete with memories and consciousness, to spontaneously arise from randomness, than for the entire ordered universe we see today to form naturally. Here's the paradox. If a Boltzmann brain is more likely than the universe itself, then statistically, it seems more probable that we ourselves are these random, fleeting brains, merely hallucinating a coherent universe around us. This leads to a disturbing possibility. Everything we know, every memory, every experience could be a product of random fluctuations, and yet we perceive it as real, as lasting, as meaningful. The Boltzmann brain paradox forces us to confront deep questions about probability, observation, and existence. It challenges our assumptions about what is typical, what is real, and what can be trusted as evidence of a larger reality. Philosophers and cosmologists debate ways to resolve the paradox. Some suggest constraints on cosmological models to prevent Boltzmann brains from dominating. Others argue it shows the limits of applying probability over infinite time scales. At its core, the Boltzmann brain paradox reminds us how fragile our sense of reality can be. It shows that even the universe itself, vast and seemingly stable, can hide unsettling uncertainties about existence and consciousness. And that is the eerie, fascinating mystery of the Boltzmann brain paradox. Maxwell's demon paradox is one of the most famous and thought-provoking puzzles in physics. It challenges our understanding of entropy, the second law of thermodynamics, and the nature of information. Imagine this. A box of gas is divided into two compartments. According to the second law of thermodynamics, the gas should naturally spread out evenly over time, increasing entropy, the measure of disorder. Now James Clerk Maxwell imagined a tiny, intelligent being, a demon. This demon sits at a trapdoor between the two compartments. It can see the individual gas molecules and selectively allow fast molecules to pass one way and slow molecules the other way. Here's the paradox. By doing this, the demon can create a temperature difference between the compartments without expending energy, seemingly decreasing entropy. And that would violate the second law of thermodynamics, one of the most fundamental principles in physics. For over a century, scientists debated the paradox. Eventually, they realized that the demon itself must process information to sort the molecules, and that information processing comes with its own thermodynamic cost. Once you account for this, the second law remains intact. Maxwell's demon paradox teaches a profound lesson. It shows a deep connection between physics and information, and it reveals that understanding entropy is not just about energy, but also about knowledge, measurement, and the act of observation itself. At its core, the paradox reminds us that even the most established laws of nature have subtle and surprising implications. It challenges our intuitions and invites us to explore the boundaries of physics, information, and reality. And that is the enduring fascination of Maxwell's demon paradox. The Banach-Tarski Paradox is one of the most mind-bending puzzles in mathematics. It challenges everything we think we know about volume, space, and geometry. Imagine this. You have a solid sphere, like a perfect ball. Now, according to the paradox, it is theoretically possible to divide this sphere into a finite number of pieces. And then, using only rotations and translations, reassemble those pieces into two identical spheres, each exactly the same size as the original. Here's the mind-blowing part. You start with one ball and somehow end up with two perfect copies of it. It seems impossible, like creating matter out of nothing. And yet, mathematically, it is allowed under certain assumptions in set theory and geometry. The paradox relies on the concept of infinite sets and the axiom of choice. These pieces are not ordinary physical objects. They are highly abstract mathematical constructs. You cannot perform this trick with real-world objects. But in the world of pure mathematics, the rules allow such counterintuitive results. The Banach-Tarski Paradox teaches a profound lesson about infinity, abstraction, and the limits of human intuition. It shows that even seemingly simple ideas like volume or matter can behave in strange ways under mathematical rules. At its core, the paradox reminds us that mathematics can be stranger than reality itself. It challenges our assumptions about space, division, and measurement, and it continues to fascinate mathematicians, philosophers, and anyone willing to explore the edge of logic and abstraction. The liar's revenge paradox is a fascinating twist on the classic liar paradox. It explores self-reference, truth, and the limits of language in ways that are both playful and unsettling. Imagine this. Someone makes a statement like, "This statement is false." This is the classic liar paradox. If the statement is true, it must be false. And if it is false, then it is true, creating an endless loop of contradiction. Now the liar's revenge takes this a step further. Suppose a person says, "Everything I say is false," or they assert a series of statements that refer to each other's truthfulness. Suddenly, the paradox multiplies. Each statement undermines the others, and the logical structure collapses into a maze of contradictions. Here's the core puzzle. How can we assign truth or falsity to statements that refer to themselves or each other in circular ways? Any attempt to do so seems doomed to fail. The statements fight back, creating an endless cycle of logical rebellion. Philosophers and logicians study this paradox to explore the boundaries of truth, semantics, and self-reference. It highlights the fragile nature of language when it tries to capture absolute truth. And it reminds us that not all statements can be neatly categorized as true or false. At its core, the liar's revenge paradox teaches us humility about reasoning and logic. It shows that language can turn against itself, and that even simple statements can produce endlessly complex and mind-bending puzzles. The invisible gorilla paradox is one of the most surprising and eye-opening puzzles in psychology. It challenges our assumptions about attention, perception, and what we actually notice in the world around us. Imagine this. You are watching a video of people passing basketballs. Your task is simple. Count the number of passes made by one team. Most people focus intently on the task, counting passes carefully. And then it happens. A person in a gorilla suit walks right through the scene. Strikingly, many viewers don't see the gorilla at all. Here's the paradox. We can focus our attention so narrowly that obvious things in plain sight go completely unnoticed. This is called inattentional blindness. It reveals that perception is not just a passive recording of reality. It is an active process, shaped by our focus, expectations, and mental filters. The invisible gorilla paradox has profound implications. It affects eyewitness testimony, driving safety, and even everyday decision-making. It shows that even when we are looking directly at something, our minds can completely miss it. At its core, the paradox reminds us that human perception is limited and selective. We see the world not as it is, but as our brains allow us to see. And that is why the invisible gorilla remains one of the most striking demonstrations of the hidden gaps in attention and awareness. The brain in a vat paradox is one of the most unsettling thought experiments in philosophy. It challenges everything we think we know about reality, knowledge, and consciousness. Imagine this. Your brain is removed from your body. It is placed in a vat of life-sustaining liquid and connected to a supercomputer that sends it electrical signals, simulating an entire reality. From the brain's perspective, everything feels completely normal. You see a world full of objects, people, and experiences, yet all of it is a simulation, a perfectly crafted illusion, indistinguishable from reality. Here's the paradox. How can you know whether your experiences are real or just signals in a vat? Every piece of evidence you have could itself be part of the simulation. Reasoning about reality becomes almost impossible. Philosophers use this paradox to explore skepticism, knowledge, and the limits of human certainty. It raises questions about perception, consciousness, and what it truly means to know something. Even the most basic beliefs about the world could, in principle, be completely mistaken. At its core, the brain in a vat paradox reminds us of the fragility of our understanding. Reality might be far stranger than it appears, and our sense of self and the world could be a carefully constructed illusion. It forces us to confront the possibility that the truth of existence may always lie beyond our direct grasp. The paradox of the observer's escape is one of the most intriguing thought experiments in quantum mechanics and philosophy. It explores the tension between observation, measurement, and the reality that exists beyond what we can see. Imagine this: a quantum system that evolves according to strict physical laws. As long as it is unobserved, it can exist in multiple states simultaneously, a phenomenon known as superposition. Now consider an observer trying to measure this system. The act of observation collapses the superposition into a single outcome. But here's the paradox. If the observer could somehow escape detection, the system would remain in superposition. Yet by attempting to avoid observation, the observer influences the system in subtle ways. This creates a strange loop. The system's behavior depends on whether it is observed, but the observer's own actions are entangled with the system. The line between subject and object begins to blur. The paradox of the observer's escape highlights the fundamental mystery of quantum mechanics. It forces us to confront the role of consciousness in shaping reality. It challenges the classical idea that reality exists independently of observation. At its core, the paradox reminds us that in the quantum world, the act of watching is never neutral. Reality is not just out there. It is a delicate interplay between what is observed, who is observing, and how observation occurs. And that is the strange, fascinating lesson of the paradox of the observer's escape. Wheeler's delayed choice paradox is one of the most mind-bending puzzles in quantum physics. It challenges our understanding of cause and effect, observation, and the nature of reality itself. Imagine this. A photon, the smallest particle of light, is sent through a device called a double-slit apparatus. If we measure which slit the photon passes through, it behaves like a particle. If we do not measure, it behaves like a wave, creating an interference pattern. Here's the twist. In Wheeler's delayed choice experiment, the decision to measure or not can be made after the photon has already passed through the slits. And yet, the photon seems to retroactively adjust its behavior based on that future choice. This creates a profound paradox. How can a particle know what measurement will be performed in the future? It seems as if the future can influence the past. And that observation is not just passive, but actively shapes reality itself. Physicists see this as a demonstration of the deep mystery of quantum mechanics. It shows that particles do not have definite properties independent of measurement. and it challenges our classical intuitions about time, causality, and reality. At its core, Wheeler's delayed choice paradox reminds us that the universe is far stranger than everyday experience suggests. It blurs the line between observer and observed, and it forces us to question whether reality exists independently or only through interaction and measurement. This paradox is a glimpse into a universe where the act of looking can change the past, where time and reality are more fluid than they seem. And that is the enigmatic lesson of Wheeler's delayed choice paradox. The unstoppable consensus paradox is one of the most fascinating puzzles in social science and philosophy. It explores how collective agreement can shape reality in unexpected and sometimes troubling ways. Imagine this. A group of people must make a decision. Over time, discussions, debates, and social pressure push the group toward a single consensus. Eventually, the group reaches an agreement that seems unstoppable. Here's the paradox. Even if the consensus is flawed, irrational, or factually incorrect, once it forms, it gains momentum, reinforcing itself through social validation. Dissenting opinions struggle to survive, and the truth may become irrelevant. This creates a troubling tension. The unstoppable consensus can create stability and coordination, but it can also lock in mistakes, biases, or harmful beliefs. The very mechanism that unites a group can undermine rationality and independent thought. The unstoppable consensus paradox teaches a profound lesson about human behavior and society. It shows that truth is not always determined by evidence alone. Social dynamics, psychological pressures, and collective reinforcement can overpower objective reasoning. At its core, the paradox reminds us that consensus is a double-edged sword. It can produce harmony and cooperation, yet it can also blind societies to error and limit innovation. And understanding this paradox is crucial if we wish to navigate the complexities of collective decision-making. Skolem's paradox is one of the most intriguing puzzles in logic and set theory. It challenges our understanding of infinity, models, and the nature of mathematical truth. Imagine this. Set theory describes the universe of all sets. In particular, it can describe incredibly large, infinite structures, like the set of all real numbers. Mathematicians prove that these sets have certain properties like uncountability, meaning they cannot be listed one by one. Here's the paradox. Skolem showed that even these uncountable sets can have a countable model when viewed from the outside. In other words, from the perspective of a larger mathematical universe, every element can be matched with a natural number. Yet inside the model itself, the set still seems uncountable to its own inhabitants. This creates a strange tension. From the outside, the set appears countable. From the inside, it is uncountable. Mathematical truth becomes relative to the model in which it is considered. Skolem's paradox teaches a profound lesson about logic and formal systems. It shows that even precise mathematical definitions can lead to surprising, counterintuitive results. It forces us to question what it means for a mathematical statement to be true. At its core, the paradox reminds us that mathematics is not always absolute. Even the concept of infinity can behave differently depending on perspective. And that is the strange, fascinating mystery of Skolem's paradox. The infinite shadow paradox is one of the most intriguing thought experiments in physics and philosophy. It explores the strange interplay between light, perception, and infinity. Imagine this. A perfectly straight object like a rod extends infinitely into space. A light source shines on it from a distance, casting a shadow on a flat surface. Intuitively, we might expect the shadow to also extend infinitely. Here's the paradox. Depending on the geometry of light and the surface, parts of the shadow can stretch beyond the limits of observation. Yet the shadow also seems bounded in certain ways, influenced by perspective and distance. Infinity appears both present and constrained at the same time. This creates a deep tension. The paradox forces us to question our assumptions about space, light, and measurement. It shows that simple concepts like a shadow can become profoundly complex when infinity is involved. Philosophers and physicists use the infinite shadow paradox to explore the limits of perception and the nature of infinity. It highlights how human intuition struggles when dealing with unbounded quantities and idealized conditions. At its core, the paradox reminds us that even in the most familiar phenomena, like light and shadow, the universe can behave in ways that defy expectation and challenge understanding. And that is the mysterious, captivating lesson of the infinite shadow paradox. The immortality transfer paradox is one of the most fascinating and unsettling thought experiments in philosophy and futurism. It explores the limits of identity, consciousness, and what it truly means to live forever. Imagine this. Technology exists that allows you to transfer your consciousness into a new body or a digital substrate. In theory, you could live indefinitely, escaping the limits of your biological lifespan. Here's the paradox. If your consciousness is copied into a new body, are you really the same person? Or is it just a perfect replica with your memories, feelings, and personality, while the original you still exists or ceases to exist? Now, consider a scenario where the transfer involves destroying the original body. Does immortality truly preserve the self? Or does it create a new individual who merely believes they are you? This paradox forces us to confront profound questions about identity and continuity. What defines a person? Memory, consciousness, physical continuity, or some ineffable sense of self? Can immortality ever be genuine if it involves replication rather than continuity? Philosophers and futurists use this paradox to explore ethics, technology, and the meaning of life itself. It challenges assumptions about survival, legacy, and what it truly means to exist. At its core, the immortality transfer paradox reminds us that the desire to live forever may be far more complicated than it seems. Immortality is not just about duration. It is about continuity, selfhood, and the delicate thread that connects past, present, and future. And that is the haunting, thought-provoking lesson of the immortality transfer paradox. The paradox of the forgotten dream is one of the most mysterious and introspective puzzles in philosophy and psychology. It explores memory, consciousness, and the fleeting nature of experience. Imagine this. You wake up from a vivid dream. The dream felt real, full of emotion, detail, and meaning. But as soon as you rise and start your day, it begins to fade. Fragments disappear. Soon, only a shadow of the dream remains. A sense, a feeling, a whisper of what once was. Here's the paradox. If the dream cannot be recalled, did it truly exist? Is the experience lost forever, or does it persist somewhere in the mind, inaccessible yet real? Our memories define reality for us, but dreams exist in a liminal space between perception and forgetfulness. This paradox forces us to confront the fragility of human consciousness. It shows that experiences can vanish even though they were once vivid and profound. The mind can create worlds that are fully real in the moment, only to erase them without warning. Philosophers and neuroscientists study this paradox to understand memory, awareness, and the construction of reality. It highlights the tension between existence and recollection, presence and absence, and it reminds us how much of our inner life is fleeting, intangible, and ephemeral. At its core, the paradox of the forgotten dream teaches us to cherish the fleeting moments of consciousness. Even if we forget them, they shape who we are. They leave subtle traces in thought, emotion, and perception. And that is the haunting, delicate mystery of the paradox of the forgotten dream. The paradox of the timeless choice is one of the most thought-provoking puzzles in philosophy and metaphysics. It explores the nature of decision-making, free will, and the flow of time itself. Imagine this. You are faced with a critical decision. The outcome will shape your life in profound ways. Yet, in this paradox, time as we know it does not exist. Past, present, and future collapse into a single, timeless moment. Here's the paradox. If all choices exist simultaneously in this timeless state, how can one meaningfully choose? Does choice require the passage of time, or can it exist independently of temporal flow? And if the future already exists in this timeless sense, is any decision truly free, or merely an illusion of agency? This paradox challenges our deepest intuitions about causality and responsibility. It suggests that the very act of choosing might be an emergent property of consciousness interacting with time, or perhaps that the flow of time itself is a construct that gives meaning to decisions. Philosophers use this paradox to explore determinism, free will, and the nature of reality. It raises questions about whether our sense of agency is intrinsic, or whether it emerges from the unfolding of events through time. At its core, the paradox of the timeless choice reminds us that choice, freedom, and time are deeply intertwined. It forces us to consider that the moments we think define us might exist outside the flow of time itself, and it leaves us with a humbling, mind-expanding reflection on what it truly means to decide, act, and exist. Maxwell's demon with information loss is an intriguing twist on the classic Maxwell's demon paradox. It explores the deep connection between thermodynamics, information, and the fundamental limits of knowledge. Imagine this. A tiny demon sits at a trapdoor between two compartments of gas. It selectively allows fast-moving molecules to pass one way and slow-moving molecules the other. Seemingly, the demon can decrease entropy, creating order from disorder without expending energy. But here's the twist. In reality, the demon must observe and record information about each molecule to decide how to act. And information itself is physical. Storing, processing, or erasing it comes at a thermodynamic cost. When the demon forgets, deletes, or loses information, entropy increases again. No matter how clever the demon is, the second law of thermodynamics remains unbroken. This paradox highlights a profound insight. It shows that information and energy are deeply intertwined. Observing and knowing are not free, and ignorance or loss of information restores balance to the universe. Physicists and computer scientists study this paradox to understand the limits of computation, measurement, and physical law. It teaches us that knowledge is not abstract. It has real consequences in the physical world. At its core, Maxwell's demon with information loss reminds us that the universe enforces order and chaos in subtle, inescapable ways. Even the cleverest manipulations cannot escape the fundamental connection between information and entropy. And that is the striking, counterintuitive lesson of this paradox. The observer-dependent causality paradox is one of the most perplexing puzzles in physics and philosophy. It challenges our understanding of cause and effect, measurement, and the role of consciousness in shaping reality. Imagine this. Two events occur in a quantum system. From one observer's perspective, event A seems to cause event B. But from another observer's frame of reference, event B appears to precede event A. Here's the paradox. Causality, the principle that one event leads to another, seems to depend on the observer's viewpoint. What one person perceives as cause and effect may look reversed, altered, or entirely ambiguous to another. This creates a profound tension between objective reality and subjective observation. It suggests that the sequence of events is not absolute, but entangled with the perspective of the observer. Time, cause, and effect are not fixed. They can shift depending on measurement and reference frame. Physicists explore this paradox in the context of relativity and quantum mechanics. It highlights the subtle ways the universe defies our classical intuitions, and it challenges the notion that events have a single, independent order in the world. At its core, the observer-dependent causality paradox reminds us that reality is deeply relational. The act of observing may shape not only what we know, but also the order and structure of events themselves. It forces us to confront a universe where causality is not universal, but intimately tied to perspective. And that is the enigmatic, mind-expanding lesson of the observer-dependent causality paradox. Fitch's paradox is one of the most fascinating and unsettling puzzles in logic and epistemology. It explores the limits of knowledge, certainty, and what it means to know something. Imagine this. A statement claims, "It is knowable that X is true." Intuitively, this seems reasonable. If something is true, we should in principle be able to know it. Here's the paradox. Fitch showed that if all truths are knowable, it leads to a startling conclusion. Every truth must already be known, even those we have not yet discovered. This seems absurd. Clearly, there are truths in the world that remain unknown to anyone at this moment. The paradox arises from the tension between truth, knowability, and epistemic possibility. It challenges our understanding of knowledge itself. How can truths exist independently if they are all, in principle, knowable? And how can we reconcile the existence of unknown facts with the assumption that everything knowable will eventually be known? Philosophers and logicians use Fitch's paradox to explore the boundaries of epistemology, logic, and the philosophy of language. It highlights the subtle ways in which seemingly innocent assumptions about knowledge can lead to deeply counterintuitive consequences. At its core, Fitch's paradox reminds us that knowledge is not simply a matter of truth, but of limits, discovery, and the structure of understanding. It forces us to confront the delicate balance between what is true, what can be known, and what is actually known. And that is the perplexing, thought-provoking lesson of Fitch's paradox. The paradox of the infinite lottery is one of the most mind-bending puzzles in probability and philosophy. It challenges our intuition about chance, infinity, and what it means for an event to be likely or unlikely. Imagine this: a lottery that goes on forever. It has infinitely many tickets, and each ticket has a chance of winning. At first, it seems that the probability of any single ticket winning is effectively zero. Yet in an infinite lottery, a winner is guaranteed to exist. Here's the paradox. How can something be both almost impossible and yet certain at the same time? The longer the lottery continues, the more tickets are drawn. And while each individual ticket seems insignificant, the infinite process ensures that some ticket will eventually succeed. This creates a strange tension between intuition and mathematics. It challenges our understanding of probability, certainty, and expectation in infinite systems. It shows that infinity can overturn the rules we rely on in finite scenarios. Philosophers and mathematicians study the infinite lottery paradox to explore decision theory, probability, and the nature of certainty. It teaches us that our everyday understanding of chance is fragile when faced with the infinite. At its core, the paradox reminds us that infinity is not just a large number. It behaves in ways that defy common sense. Even events that seem impossible can become inevitable. And that is the strange, fascinating lesson of the paradox of the infinite lottery. The paradox of the infinite library is one of the most mind-expanding puzzles in philosophy, mathematics, and information theory. It explores infinity, knowledge, and the limits of what can ever be known or discovered. Imagine this: a library that contains an infinite number of books. Every book is filled with every possible combination of letters, words, and sentences. Some books are complete nonsense, while others contain perfect truths, histories, or secrets of the universe. Here's the paradox. In this infinite library, every possible piece of knowledge exists somewhere. But because it is infinite, finding any meaningful book becomes effectively impossible. The more you search, the more overwhelming the library becomes, and certainty or understanding seems to vanish. This creates a strange tension. Infinite knowledge exists, yet it is practically inaccessible. Every truth, every story, every solution is encoded somewhere, but the vastness makes it unreachable. It shows that existence alone does not guarantee comprehension. Philosophers and mathematicians study the infinite library paradox to explore information, probability, and human understanding. It highlights the limits of discovery and how infinity can render certainty both present and meaningless at the same time. At its core, The paradox reminds us that even in a universe of infinite possibility, meaning is fragile and discovery requires more than mere existence. It forces us to confront the relationship between knowledge, accessibility, and comprehension. And that is the mesmerizing, humbling lesson of the paradox of the infinite library. The friendship paradox is one of the most surprising and counterintuitive puzzles in social science and network theory. It explores how our perceptions of social connections can be misleading, and how statistics can reveal hidden truths about relationships. Imagine this. You look at your friends and notice something strange. Most of your friends seem to have more friends than you do. At first, this feels impossible. How can the majority of people have more friends than the average person? Here's the paradox. Mathematically, it occurs because people with more friends are more likely to be your friend. Highly connected individuals appear in many people's social circles, skewing our perception of average connectivity. So even if you are perfectly average, your friends are statistically likely to be above average. This creates a fascinating tension between perception and reality. It shows that our social intuition can be biased by the network structure itself. The paradox applies to social networks, online communities, and even patterns of influence or information spread. Researchers use the friendship paradox to study sociology, epidemiology, and network dynamics. It teaches us that understanding society requires careful analysis of patterns, not just casual observation. At its core, the friendship paradox reminds us that reality is often stranger than it seems. Your experience of the world may be influenced more by statistical bias than by objective measures, and it highlights the subtle ways networks shape perception, influence, and social experience. That is the intriguing, thought-provoking lesson of the friendship paradox. The observer's paradox is one of the most fascinating and perplexing puzzles in physics and social science. It explores how the act of observation can fundamentally change the phenomenon being observed. Imagine this. You are trying to measure or witness a system. From a quantum particle to a social experiment, the moment you observe, the system reacts. Its behavior shifts, adapts, or collapses into a specific state, influenced by your very attention. Here's the paradox. Observation is necessary to gain knowledge. Yet the act of observing can prevent us from seeing the system as it truly exists independently. In other words, the more we try to study reality, the more we may distort it. This creates a profound tension between knowledge and influence. In quantum mechanics, it appears as the measurement problem. Particles act differently when observed. In social sciences, survey participants behave differently when they know they are being studied. Observation becomes a double-edged sword, both revealing and altering truth simultaneously. Philosophers and scientists study the observer's paradox to explore the limits of measurement, perception, and reality itself. It teaches us that knowledge is never purely passive, and that awareness and intervention are intertwined. At its core, the paradox reminds us that reality is not entirely separable from perception. The act of watching shapes what can be known, and certainty is always entangled with influence. And that is the haunting, thought-provoking lesson of the observer's paradox. Benford's law paradox is one of the most surprising puzzles in mathematics and statistics. It explores the hidden patterns in numbers and challenges our intuition about what random really means. Imagine this. You look at a large collection of numbers from everyday life, financial data, populations, or physical constants. You might expect that the first digits from 1 to 9 appear equally often. After all, shouldn't randomness be uniform? Here's the paradox. Benford's law shows that smaller digits appear as the first digit far more often than larger ones. The number 1 shows up about 30% of the time, while 9 appears less than 5% of the time. This pattern holds across many real-world datasets, from rivers' lengths to accounting figures. Why does this happen? It arises because numbers grow exponentially, and logarithmic scales skew the distribution of leading digits. What feels random, to our intuition is actually structured and predictable when viewed mathematically. Benford's law paradox highlights the hidden order in seemingly chaotic systems. It has practical applications in fraud detection, data science, and forensic accounting. It reminds us that our intuition about randomness is often misleading. At its core, the paradox teaches us that patterns exist even in places we assume are purely random. It shows the subtle beauty of mathematics hidden in everyday numbers. And that is the fascinating, counterintuitive lesson of Benford's law paradox. Quine's paradox is one of the most intriguing and mind-bending puzzles in logic and philosophy of language. It explores self-reference, truth, and the limits of formal systems. Imagine this. A sentence refers to itself in a clever way. For example, consider the sentence, "Yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation." At first glance, it seems like a normal statement, but then the paradox emerges. Here's the paradox. If the sentence is true, then what it asserts must also hold, making it false. If it is false, then it is actually true. The statement loops back on itself, creating an endless cycle of contradiction. Quine's paradox is closely related to the classic liar paradox, but it highlights the role of language and quotation in creating self-reference. It shows that even formal systems can produce statements that defy consistent truth evaluation. Logic alone cannot resolve the paradox without careful rules about self-reference and meta-statements. Philosophers and logicians study Quine's paradox to explore the foundations of truth, meaning, and formal reasoning. It challenges our assumptions about how language can represent reality. At its core, the paradox reminds us that truth is not always straightforward. Self-reference can twist language into loops that defy intuition and certainty. And that is the fascinating, confounding lesson of Quine's paradox. Hilbert's Grand Hotel Paradox is one of the most famous and mind-bending thought experiments in mathematics. It explores infinity, accommodation, and the counterintuitive properties of infinite sets. Imagine this: a hotel with infinitely many rooms, all of which are occupied. A new guest arrives, hoping for a room. Intuitively, you might think the hotel is full and there's no room left. Here's the paradox. Even though every room is occupied, the hotel can still accommodate the new guest. The manager simply moves the guest in room 1 to room 2 to room 3, and so on. Every current guest shifts up one room, freeing room 1 for the newcomer. It gets even stranger. If infinitely many new guests arrive, the hotel can still accommodate all of them. By moving each existing guest from room N to room 2N, all the odd-numbered rooms become free for the infinite new arrivals. Hilbert's Grand Hotel Paradox highlights the counterintuitive nature of infinity. It shows that infinite sets behave very differently from finite ones. Infinity is not just a large number, it is a concept that defies normal intuition. At its core, the paradox teaches us that our everyday understanding of full and empty breaks down in the infinite realm. It forces us to rethink what is possible when dealing with infinite quantities. And that is the astonishing, mind-expanding lesson of Hilbert's Grand Hotel Paradox. The Bootstrap Paradox is one of the most fascinating and perplexing puzzles in time travel and philosophy. It explores causality, identity, and the strange loops that arise when the past and future collide. Imagine this. A person travels back in time and gives a piece of information, a book, or an invention to someone in the past. That item becomes the origin of itself, with no clear point of creation. It exists in a loop, seemingly without an origin, passed from future to past and back again. Here's the paradox. If the item has no origin, where did it really come from? It seems to exist eternally, with its existence sustained solely by the time loop. Cause and effect twist in on themselves, defying our normal understanding of history and creation. The Bootstrap Paradox highlights deep questions about time, free will, and the nature of reality. It challenges our assumption that every effect must have an independent cause. In these loops, The boundaries between creation and consequence blur, creating a universe of strange, self-sustaining events. Philosophers and physicists use the paradox to explore temporal mechanics, logic, and the implications of time travel. It forces us to confront a world where beginnings and endings may not exist in the way we imagine. At its core, the Bootstrap Paradox reminds us that time may be far stranger than it appears. The future can influence the past, and the origins of things can vanish into a loop of causality. And that is the mind-bending, thought-provoking lesson of the Bootstrap Paradox. Simpson's paradox is one of the most surprising and counterintuitive puzzles in statistics and data analysis. It explores how trends can reverse when data is combined or broken into groups. Imagine this. You are comparing two treatments, A and B, across different groups of patients. Within each group, treatment A seems better than treatment B. Yet when you combine all the data, treatment B appears to outperform treatment A overall. Here's the paradox. How can something that is true in every subgroup be false when aggregated? The answer lies in hidden variables, weighting, and the influence of context on statistics. Aggregated data can mislead if we ignore the structure of the groups within it. Simpson's paradox highlights the subtle dangers of interpretation in data. It teaches us that context matters, and that averages or totals can hide important truths. This paradox is not just theoretical, it appears in medicine, social science, and even everyday decision-making. At its core, Simpson's paradox reminds us to question assumptions and look deeper than surface numbers. It shows that reality is often more complex than it first appears. And that is the fascinating, cautionary lesson of Simpson's paradox. The paradox of choice is one of the most thought-provoking puzzles in psychology and decision-making. It explores how freedom and abundance can sometimes make life more difficult rather than easier. Imagine this. You walk into a store filled with hundreds of options for a single product. At first, you feel excited. The possibilities seem endless. Yet as you try to decide, confusion, doubt, and anxiety start to creep in. Here's the paradox. While having choices is generally considered a good thing, too many options can overwhelm the mind. People may procrastinate, make worse decisions, or feel less satisfied even after choosing. The very freedom that should empower us can lead to stress, regret, and indecision. The paradox of choice highlights the delicate balance between autonomy and cognitive overload. It teaches us that more is not always better. Sometimes limits and constraints can actually improve satisfaction and clarity. At its core, the paradox reminds us that decision-making is deeply psychological, not just rational. The abundance of options can be a hidden trap, shaping our happiness in unexpected ways. And that is the fascinating, eye-opening lesson of the paradox of choice. The paradox of the court is one of the most intriguing puzzles in law, ethics, and logic. It explores contracts, obligations, and the surprising ways reasoning can twist expectations. Imagine this. A law student makes an agreement with a teacher. The student promises to pay tuition after winning their first case in court. It seems straightforward at first, but the situation soon becomes paradoxical. Here's the paradox. If the student wins their first case, they must pay the teacher according to the contract. But if the teacher sues to claim payment, and the student loses the case, then they are not required to pay until winning a case. The very act of enforcing the contract creates a loop where neither party can clearly win or lose. The paradox of the court highlights the tension between legal reasoning and real-world obligations. It shows how logic, contracts, and human behavior can interact in unexpected, circular ways. The paradox has fascinated philosophers and legal theorists for centuries, as it reveals the limits of strict rules in complex situations. At its core, the paradox reminds us that agreements, promises, and laws exist within context. The interplay of logic and circumstance can create situations that defy straightforward resolution. And that is the intriguing, mind-bending lesson of the paradox of the court. The arrow paradox is one of the oldest and most thought-provoking puzzles in philosophy, dating back to Zeno of Elea. It explores motion, time, and the very nature of change itself. Imagine this. An arrow is flying through the air toward its target. At every single instant of time, the arrow occupies a specific position. It seems perfectly still in that instant, not moving at all. Here's the paradox. If at every instant the arrow is motionless, how can it ever move? Motion appears impossible when you break time down into indivisible moments. Yet in reality, arrows do reach their targets, rivers flow, and people move. How do we reconcile the math of instants with the experience of continuous motion? The arrow paradox highlights deep questions about time, continuity, and the limits of human intuition. It challenges the notion that dividing time into smaller and smaller slices can fully explain motion. Philosophers, mathematicians, and physicists have wrestled with this paradox for millennia, leading to ideas about calculus, limits, and the continuum. At its core, the paradox reminds us that reality is more than the sum of static snapshots. Movement, change, and time flow in ways that challenge simple logic. And that is the enduring, mind-expanding lesson of the arrow paradox. The whole paradox is one of the most intriguing and counterintuitive puzzles in mathematics and philosophy. It explores the strange nature of absence, space, and the relationship between things and the gaps they leave behind. Imagine this. You have a perfectly solid object like a block of metal. You cut a hole in it. A void, an absence of material, appears where the metal used to be. Here's the paradox. The hole itself seems to have properties. It can be measured, shaped, or moved, but it is literally nothing. It has a location, a boundary, and even a size, yet it is fundamentally the absence of something else. How can nothing behave as if it is something? The whole paradox challenges our intuition about existence and non-existence. It shows that absence can have structure and influence, and that gaps can carry meaning just like matter. Philosophers and mathematicians use this paradox to explore topology, space, and the ontology of negative entities. At its core, the paradox reminds us that reality is not just made of things, but also of the spaces between them. Nothingness is not empty of significance, and absence can shape the world in profound ways. And that is the fascinating, mind-expanding lesson of the whole paradox. The Omnipotence Paradox is one of the most famous and mind-bending puzzles in philosophy and theology. It explores the limits of power, logic, and the concept of being all-powerful. Imagine this: a being that is truly omnipotent, capable of doing anything, anywhere, at any time. It seems straightforward at first. Unlimited power should mean no restrictions, no limits. Here's the paradox. If an omnipotent being can do anything, could it create a stone so heavy that it cannot lift it? If it can create such a stone, there is something it cannot do: lift the stone. If it cannot create the stone, then there is something it cannot do: create the stone. Either way, omnipotence seems to lead to a logical contradiction. The Omnipotence Paradox highlights the tension between absolute power and the constraints of logic. It forces us to ask whether true omnipotence is logically possible, or whether power must be understood in relation to reason and coherence. Philosophers and theologians have debated this paradox for centuries, exploring nuances in definitions of power, possibility, and infinity. At its core, the paradox reminds us that even the concept of limitless power has boundaries when confronted with logic. It challenges our intuitions and invites us to think deeply about the nature of ability, reason, and the ultimate limits of what can exist. And that is the thought-provoking, mind-expanding lesson of the Omnipotence Paradox. The paradox of free will and omniscience is one of the most profound and challenging puzzles in philosophy and theology. It explores the tension between human freedom and the knowledge of an all-knowing being. Imagine this. An omniscient entity exists, one that knows everything, past, present, and future. It knows every decision you will ever make, every choice you will ever face. At the same time, you feel free to make your own choices, acting independently, shaping your destiny. Here's the paradox. If the future is already known completely, can your choices truly be free? Does foreknowledge mean that your decisions are predetermined, or is there still room for genuine autonomy? If your choices are already known, it seems they cannot be otherwise. Yet the very concept of free will requires that you could have chosen differently. This paradox challenges our understanding of time, knowledge, and moral responsibility. Philosophers and theologians have debated whether omniscience and free will are compatible, proposing ideas like conditional foreknowledge, multiple timelines, or compatibilism. It forces us to consider whether freedom is about the absence of constraint or the perception of agency within a structured universe. At its core, the paradox of free will and omniscience reminds us that certainty and freedom may be entangled in ways we cannot fully comprehend. It highlights the delicate balance between knowledge, choice, and responsibility. And that is the mind-expanding, thought-provoking lesson of the paradox of free will and omniscience. The paradox of omniscience is one of the most intriguing puzzles in philosophy and theology. It explores the limits of knowledge, the nature of time, and the apparent tension between knowing everything and the unfolding of events. Imagine this. An omniscient being exists, one that knows all things past, present, and future. At first, this seems all-powerful and absolute. Nothing is hidden, nothing is uncertain. Here's the paradox. If the being already knows everything that will happen, how can free will exist? If actions are known in advance, are they truly chosen, or are they predetermined? Knowledge of the future seems to conflict with the possibility of change or genuine choice. This paradox challenges our understanding of time, causality, and responsibility. Some philosophers propose that omniscience may not conflict with free will if knowledge does not cause the events it predicts. Others explore ideas of multiple timelines, conditional knowledge, or the limits of human comprehension in understanding omniscience. At its core, the paradox of omniscience reminds us that knowing everything is not as simple as it sounds. Absolute knowledge appears to clash with freedom, uncertainty, and moral responsibility. It forces us to grapple with profound questions about the nature of reality, time, and the limits of understanding. And that is the thought-provoking, mind-expanding lesson of the paradox of omniscience.